Light bends, bounces, and breaks into patterns to reveal the hidden rules of our universe. In this video, we'll uncover the mysteries of optics, how diffraction spreads waves out, how reflection turns them around, and how refraction causes them to bend through new paths. Get ready to see the physics of light in action, from shimmering rainbows to laser precision. Optics is the study of light, specifically its interactions with matter and how it propagates through various media. This will cover various applications like lenses, microscopes, and mirrors, but before we get to those, we really need to understand how light actually interacts with matter. So we'll need to remember everything that we've already learned about light waves so far. These are electromagnetic waves in a particular region of space where the electric field and magnetic field are coupled together. And of course, the energy of an electromagnetic wave can be calculated using Planck's constant times the frequency. And in a vacuum, an electromagnetic wave will travel at the speed of light, c. Now, to really understand the history of light, we need to think a little bit about what these scientists were thinking maybe 200 or 300 years ago. Between you and I, we've taken it for granted that light is an electromagnetic wave, but for a long time, people argued over if light was actually a wave or if light was a particle. There's these two different ideas here. Isaac Newton, who was a big dog at the time, believed that light was composed of particles, and you can sort of see his model down here. The particle model envisions that each bit of light can be separated into some type of a light particle that carries the light, and under this theory, we would think that light undergoes collisions just like billiard balls would. Light cannot penetrate through an object just like other particles cannot penetrate through objects as well. But another scientist came along named Huygens, who challenged Newton and said, I actually don't think that light is made up of particles, tiny little billiard balls or baseballs that carry the light. Instead, I think light is made up of waves and these small wavelets where we could cut that light wave into a smaller wavelet that is propagating outward from a source as well. And this led to the wavelet theory of light by Huygens. It's important to note that waves are distinctly different from objects. Waves have a wavelength and frequency and repeat themselves. Waves are capable of superimposing on top of another wave such that they add together their displacements. Particles don't do that. And waves are also capable of penetrating into a new medium based on how it might be reflected or transmitted as it crosses from one medium to another. So these are all phenomena that are unique to waves, and these are all phenomena that light actually exhibits. So Huygens' principle is actually a little bit tricky to think about, but it essentially says that each part of a wave, a light wave, can be cut or separated into a smaller wavelet. And every single point on a wave, everywhere along the crest of a wave or some wave front, we could cut that wavefront into individual smaller pieces that are the source of an individual wavelet. And in this way, when we cut a light wave up, we can see that each of the individual wavelets coming from one point on the wave will all add up together. And if we think about cutting this wavefront into infinitely many smaller sources of small wavelets, we see that the spherical wavelets, these small semicircles, essentially superimpose on top of one another to create the next wavefront. So if we think about cutting a wave of light into an individual little section, that one point on the wave will act like a source of a light wave that travels outward in a spherical path. Just like if we were to drop a stone in the middle of a water pond, we would see that one individual wave would travel outward in a spherical path. The same type of thing can be done for light, except if we just cut out one small little slice of that light, it itself can be the source of a spherical wavelet. And these many spherical wavelets superimpose on top of one another to create what we call a wave front. And that's really the point that we measure the light wave from. So each of these lines right here, these vertical lines, is a wave front. That's sort of like the crest of each successive wave front, and so that's how we'll end up thinking about light waves. In this way, if I was to take these wave fronts on the left side and only let through one individual point of that wavefront, we would see that that small little section that I allowed to let through this barrier that I examined would travel outward in a spherical path. So this straight wavefront of a light wave that's traveling in one direction, if I just let one small part of it through, it actually is a spherical type of pattern, and this spherical wavelet travels outward in a spherical path from that small point. So that point on the wave acts like a source of a small spherical wavelet, and many points add up to many sources that add up to many wavelets that add up to the overall wavefront. This idea of cutting waves into their individual wavelets is actually the phenomenon that is responsible for waves spreading out as they pass through an opening or interact with some type of obstacle. So let's just think about this for a sec. When a wave passes through a large opening, we can say that it spreads out and enters into the room. But this is a little bit different between sound and light waves. We've learned about sound before, we've learned about light. If we think about a doorway right here, and we propose that light is a wave, well, we would expect for the light wave to sort of spread out as it goes through this doorway. But we don't actually see that. For light, we end up seeing a sharp shadow and just like a spotlight shining through only where the opening is. So we would say that no light will bend around the corners for this large opening. And that's a little bit different than sound. With sound, we know that if I'm standing at the edge from an opening and I am not necessarily, I'm in the shadow of that sound wave, we would know that the sound wave, when it comes to that doorway, it will actually spread out and into the next room, and a listener who was in the shadow of the sound would end up hearing that sound. So there's something weird going on here. When sound passes through a doorway, the sound spreads out into the next room. But there is something different between sound and light. Light has a very small wavelength and sound has a very large wavelength, somewhere on the size of like meters for the wavelength of sound. But with light, we're talking about nanometers for most of the different electromagnetic waves. So we see that there is a spreading out type of phenomena, which we call diffraction. We would say waves diffract, and this only occurs when the wavelength of the wave is on the same size scale as the object that it's interacting with. If we got a really small wavelength traveling through a very large object, we would expect to see no bending, no diffraction. But if we have a large wavelength traveling through a large opening, we would expect for that wave to spread out and bend as it goes through that obstacle. The bending of light waves around an opening or obstacle is called diffraction. And this is ultimately a consequence of Huygens' principle. If I just bring this opening smaller and smaller until it's roughly on the size scale of the wavelength of light, we can see that that opening would act as a source of an individual spherical wavelet, and that spherical wavelet would sort of bend around the opening, filling up the new room. But as I create a larger opening, as I widen this opening and I send that small wavelength wave through, we notice that the bending becomes less pronounced. It's diminished as the size scale of the opening increases. And for a very large opening, we would see very little bending, except for maybe right around the edges of the wave phenomena. But mostly, there's not really much diffraction happening for a large opening. And this idea of diffraction is unique to waves only. Particles like baseballs and billiard balls and cars, those do not bend and spread out as they go through an opening about the size of their length. So this is a unique phenomena that is specific to waves. If something experiences diffraction, that indicates that it is a wave-like phenomena and not an object or particle. And so as we shrink down the opening that we're sending these waves through, we would notice that there's a little bit of bending around the edges, right? Most of the light kind of going straight through. You would expect a spotlight or something like that, or if this is a sound wave, you'd expect like a loud sound all along that line. But even as we go more toward the edges, the sound wave does bend and sort of fill the room, even though there's a wall there preventing the light from going through or the wave from going through. Now, if you also look very closely, there's even something sort of more unique about this pattern going on. For the keen observer, you will notice that there sort of is like a line along this pattern. Let's see, that feels about right. And maybe another line where there's like only gray. There's no actual waves, sort of. And then there's larger waves, sort of kind of not along that line, right? So there's sort of a line right there where there's really not many waves, but maybe along these lines there's sort of less waves, and in between the waves are more pronounced. Perhaps you didn't quite see that, but there's even something more unique going on aside from just the bending. It's almost like the waves that are bending in the new room are interacting with themselves. One of the most famous experiments that proved that light is a wave-like phenomena is called the double-slit diffraction experiment. This diffraction experiment essentially has two slits in like a window or some type of filter, a double slit, which are very small openings that allow light to go through the opening. And you might think that if light behaves like a particle, it just goes straight through the opening and it gets blocked out everywhere else. So you might expect to see on the other side of this filter or this slit window, you might expect to see something like this spotlight where we just have two bright lines going through the openings. But this is wrong. This is not what we see with light traveling through two very small slits. Instead, what we see is something very strange. We see a series of bright lines in the shape of the slit, and in between those bright lines, there's complete darkness. We see bright lines on this projection screen behind the slit window, and also those bright lines are separated by like a dark line as well. Not just two bright spots like you might expect for a double slit window, but instead many, many bright spots spreading out as if there's some type of special phenomenon going on. And what we call this is an interference pattern. If the wave-like nature of light really is true to it being a wave, then we would expect for the light coming from each of these two slits to sort of act like sources of spherical wavelets, and those would interfere with each other to find moments of constructive interference and destructive interference. So again, this is a little bit of a tricky idea to wrap your head around, but we're going to send light toward this double slit window right here, and here's slit 1 and here's slit 2. As we send that wave front in through that very small slit, each of those slits will act like a source of spherical light wavelets. And that means that there will be crests that we could draw out over time as solid lines coming from the first source, and crests as solid lines coming from the second source. And there will be points where our crests line up. You'll see that there are points right here where we have both of the waves coming from slit 1 or source 1 and slit 2 or source 2, and the crests line up perfectly with each other. Two waves line up perfectly with each other, meaning that there will be constructive interference when these two wavelets coming from these two different sources are aligned. And in fact, everywhere along this line in the center, we expect for crests of the wave to always be aligned perfectly, leading to constructive interference with a maximum amplitude and displacement in the electric field and magnetic field at that time. That means that all along this line, all of the crests of the light waves will be aligning, leading to a more intense light, a brighter light. And we call this bright spot a bright fringe or a maxima in the interference pattern. This is where waves are perfectly aligned, experiencing constructive interference. Now, there will also be points in space where the slits are emitting waves such that a crest ends up lining up with a trough. These two different light sources are sending out waves until they sort of are both at opposite displacements. One's up high with a crest and one is down low with a trough. And we would expect for, at that point where a dashed line is lined up with a solid line, to lead to a minimum in the light intensity. In fact, we would have perfect destructive interference that leads to what we call a dark fringe or a minima in the interference pattern. And that is locations in space where the two slits each emit light that happens to be perfectly anti-aligned. It just happens that the difference in distance to this minimum point from slit 1 to slit 2 is a perfect path length difference that leads to these two waves being perfectly out of phase with each other. Perfect destructive interference. And it turns out that the pattern, the interference pattern that we get, will alternate between having perfect constructive interference at the center and then perfect destructive interference, darkness, and then perfect constructive interference again, bright, and then perfect destructive interference again, dark. And so if we trace out sort of where all of the individual wavelets are aligned with each other and anti-aligned with each other, you will end up getting what we call an interference pattern that we could project onto a screen beyond this double slit window that says something about the physics going on with the light. We have alternating bright spots and dark spots. And notice that these patterns are very small, so it's a really hard measurement to make with just your eyes. You know, if we had very precise tools and lasers, we could make these measurements very precisely. But imagine making these measurements on the millimeter scale way back in the day when we didn't have lasers. This was a difficult experiment to run, and this was really mind-bending for a lot of scientists at the time. So let's keep thinking about this. We have wave fronts of light, continuous light waves being sent toward a double slit window or like a filter. And we would see that at each of these points, this first slit acts like a source of one set of wavelets, and the second slit acts like a source of other wavelets. And if we think about both of those wavelets traveling, simultaneously, what we end up getting is a pattern, something like this that you see on the right side of the double slit window. And everywhere along this center line, you'll notice that the waves are aligned. They are leading to a maximum in the center. And then everywhere along this dashed line, we are getting a minimum. And everywhere along this dashed line, it's symmetrical. There's a maximum in the middle that we get if we were to project this light onto some screen beyond the filter window. And then next to that middle maximum, there's going to be two dark spots, a minimum, and then we have a maximum again all along this solid line, and it's perfectly symmetrical. And then it just so happens, based on the geometry and wave-like nature of light, that we get another minimum, a dark spot right here, and then a bright spot. And so this interference pattern that you can project onto a screen is indicative of the wave-like nature of light, and it can tell us something about the measurements that we can make from these two, the light waves coming from these two slits. Essentially, because the slits are different distances away from each of these points of interest, let's just say we got a point of interest P up here, because the light waves have to travel a different distance between slit 1 and slit 2, if I'm looking at this minima as my point of interest, we would have like light waves traveling all the way to that point of interest, and light waves, an individual wavelet with high and low displacement at various points in time traveling to that point of interest. And these two waves could either be aligned with each other or anti-aligned. So there will be a phase difference based on the path length difference. We can calculate if these two sources will have waves that are in phase or out of phase based on this difference in path length that they need to travel. Clearly, source 2 has waves that travel a little bit longer than source 1, and the phase of these waves might be in phase or out of phase. In this case, we would find that they were perfectly out of phase because this point P is a minima right here. And so that would mean that we have a phase difference of something like pi radians or 180 degrees between these two waves coming from these two sources. Now, hopefully you're seeing this double slit experiment come together, because this is actually the basis for many of the experiments that are done with regards to optics. And so if you don't understand this double slit experiment, I encourage you to go back and retake a look at it so that you can understand, because the next stuff is going to build off of this. But essentially, one more time, we have a light source that is sending out coherent light, essentially light that's all sort of in phase with each other. At first, when it hits this double slit window, or filter as I like to call it, it sends light waves out from both of those slits, and at various points in space beyond the window, there will be times where the light waves from the top slit are aligned or anti-aligned with the light waves from the bottom slit. Different points in space will give us an alternating set of bright fringes and dark fringes, maxima and minima, correlated with constructive interference when the two sources have waves that are in line with each other, and destructive interference for the minima when the two sources send waves out that are out of phase with each other and anti-aligned with each other. So you don't need to really be able to draw out these semicircular wavelets, but you do need to understand how we come up with an interference pattern and what the bright spots and dark spots actually mean. It turns out for the double slit experiment, the reason why we look at that is because it ends up giving a very symmetrical pattern that's relatively easy to understand, and the intensity diminishes very consistently as we move outward from this middle bright spot that I have circled. So it turns out that this diffraction experiment and this interference pattern can be used to say something about the wave-like nature of light. Let's label a few ideas with this interference pattern. First off, we'll have our double slit window here, and that double slit window will ultimately have a slit separation distance, lowercase d. However far apart those slits are, will say something about the way the light waves spread out as they diffract through this window. And then we label this middle bright spot the central maximum, and that's like our reference point where we'll always measure the interference pattern with reference to our central maximum. So, to obtain constructive interference in this double slit experiment, to find the locations of the bright fringes, we can use the diffraction equation that you see in red here, where lowercase d is the slit separation between the two slits. Theta m is a diffraction angle to a particular bright spot. M here is known as the order of interference. It's like a label that we use to keep track of which bright spot we're talking about, and lambda is the wavelength of the light. So again, D is the slit separation distance between these two slits in the double slit experiment. Theta M is tracking the angle to which particular bright spot you're looking at. This middle bright spot would have an M equal to 0. M is the order of interference. It's just a label that we use to keep track of which bright spot in the pattern we're looking at. M equals 0, that's the middle bright spot. That's the central maximum. And if I go up from there, M has to be an integer value. It can be positive or negative. But if I just say M equals +1, that means that I'm looking at the bright spot that is one place next to the central maximum. And if I was to look at the M equals -1, that means that I'm looking at the bright spot in the other direction from the central maximum right next to it. So M equals 0 is the middle bright spot. M equals +1 is the bright spot right next to it, and M equals -1 is the bright spot right next to it in the other direction, and then it moves outward from there. +2 and -2 is farther spread, and so on. And these M values can take on any integer value that can be positive or negative, including 0, and theoretically, the diffraction continues infinitely up to infinite values of M, although there is a true realistic limit depending on how far the light could actually bend. So let's take a further look at these equations. We can also calculate for the destructive interference locations, the dark fringes, by using the diffraction equation, and it just looks slightly different with the slit separation distance lowercase d, theta m being the angle of diffraction toward a minima, a dark spot, and m is still the order of interference that tracks which dark spot we're looking at, but now we have a +1/2 in here times the wavelength. And essentially what this means is the dark spots will be halfway in between all of the bright spots. And so we still use the numbers M to keep track of these, so it gets a little tricky, but this bright spot right here would be the M equals -1 bright spot, right? If we had M equals -1, it would be like we were at -1/2 between the 0 and -1. So to find the dark spot, you would plug in M equals -1 to find in between 0 and -1. And to find the dark spot between 0 and 1, you would end up plugging in M equals 0 for that one. That way you would have half of a wavelength difference between the M equals 0 and +1. So these equations are definitely a little bit tricky. M still is an integer value that just kind of tracks which bright spot or dark spot you're looking at, depending on if you're using the red or green equation. And all of your variables are labeled down here with their SI units. So make sure you spend some time really taking in what I mean with theta M and M being the order of interference. Now, if we look at this double slit window and the projection screen over here, we could assign a length L, which is the horizontal distance between the double slit window and the projection screen. And so we call that the projection length, which is measured in meters. And just by using a simple trig function of tangent, we can figure out that using that diffraction angle, we could determine the actual true y distance, the slits, the fringe spacing y between each bright fringe in reference to the central maximum. So ym is a distance from one bright spot to the central maximum. We call that the fringe spacing, and it's measured in meters and can be solved for with this simple trig function of tangent equals opposite over adjacent. Now, there is one math trick that you might see coming up in double slit diffraction, and that's called the small angle approximation, which is essentially, since we have an equation that involves sine and we have an equation that involves tangent, it's important to note through trigonometry and geometry, we can say that essentially the small angle approximation says that the sine of theta will be equal to the tangent of theta for very small angles. Essentially, angles somewhere below 15 degrees will cause for the sine of theta to exactly equal the tangent of theta. You can plug this in your calculator, but the approximation gets weaker and weaker. It's less close approximation as we get to larger and larger angles. If you plug in sine of 1 degree, it will end up being very close to the result that you get for tangent of 1 degree. And so this essentially means that we can take our d sine theta equals m lambda equation, that's the diffraction equation. We got a sine theta in there, and we can also use the tangent equation that we just spoke about and set those equal to each other for small angles, which is usually what we'll have for diffraction. And that basically means that if we are using the small angle approximation, we can set everything that the sine was equal to everything that the tangent was equal to. And so m lambda over d ends up equaling y sub m over L in this case, as long as we have small angles. All right, so let's try an example with double slit diffraction. Here we have a green laser that's sending a wavelength of 532 nanometer light toward a double slit window with a projection length of 1 meter between the window and the screen. And the spacing between the interference maxima is 2.3 millimeters. So let's actually label what that last variable is. That is saying that the spacing between the maxima, the delta y between like any bright spots, any two bright spots from like 0 to 1, let's say, is going to be 0.0023 meters. I like to get everything in the standard units. So whether we're talking about the spacing between the 0th bright spot and the first bright spot doesn't really matter. In a double slit diffraction experiment, that spacing is actually consistent between each of those bright spots. So any of these delta y's will end up being the same. And so basically I have the difference in my fringe spacing between the central maximum and the next maximum. So we're asked to solve for the slit spacing d. So I think we're going to need to use our diffraction equation. Let's go ahead and write that one out. We got d sine theta equals m lambda. That's for the bright spots. And that's what we're basically given information for. The interference maxima are separated. So that's our bright spot equation. And we also know that there's a trig function that can relate the diffraction angle to the slit spacing. Well, if I was to calculate the distance to the first maximum, this would basically be the distance to the m equals 1 bright fringe from the central maximum. So we can plug that number in for our y here, and we have a value for L, so we can solve for our diffraction angle to like the first bright spot. So here I'm getting a theta 1 of 0.13 degrees. Now that is certainly a small angle for that first diffraction bright spot. So we can go ahead and plug that back into our diffraction equation and hopefully solve for lowercase d. And here I'm getting a result of 2.34 times 10 to the minus 4 meters. These double slit windows are on a very small scale, similar to the wavelength of the light, right? This wavelength is about 10 to the minus 9 meters, maybe 10 to the minus 7 or so. And this wavelength right here is at about 10 to the minus 4. So those are roughly in the same ballpark, about 1,000th off. And so we'll start to see some diffraction in this regime. Lastly, I would like to mention that since this is a small angle, we can use the small angle approximation to sort of skip a step. Small angle approximation says that as long as this angle is very small, the tan of theta is equal to the sine of theta. And so we can sort of set those equal to what we saw in the previous slide, which said that m lambda over d is equal to ym over L. And so if I rearrange and solve, I will end up getting d is equal to m lambda L over y. And so that would be like for the first bright spot, we got our wavelength 532 times 10 to the minus 9 meters times 1 meter divided by our spacing, which is just 0.0023 meters. And here you would see that we would get the same answer as what you found in the green. Now, in truth, diffraction occurs for more than just a double slit experiment. But if you understand double slit diffraction, you're probably mostly set for the rest of the phenomena that we're going to discuss with respect to diffraction. So you really want to make sure you understand the double slit because it's the simplest one. But there are other types of diffraction too that we could run experiments on and measure. One type of diffraction object is a diffraction grating, which is like a window that has many slits. Multi-slit diffraction is what this is often called. And it's very similar to double slit diffraction, except instead, each individual slit on a diffraction screen or grating will act as an individual source of waves. And what we notice for the interference pattern is that we do still have a central maximum of white light. If we're shining white light, which has all the different wavelengths into this diffraction grating, our central maximum will have white light. We'll have a dark spot next to the central maximum, but then our first maxima, the first bright spot, the first order maxima will not appear as just a white spot. Instead, the wavelengths of the light will be slightly separated, producing a multicolored bright fringe along the spectrum of the visible light spectrum, or the rainbow. So to track these bright spots, these rainbow bright spots, we still use the diffraction equation. It's actually the same one as the double slit experiment. To find the constructive locations where we see bright fringes for a diffraction grating, you use the same diffraction equation with m being integer values, including 0 and including negative values. And you can still use the simple trig function of tan theta equals the fringe spacing divided by the projection length. But one thing to note is that you'll often be given a diffraction grating, which does not actually have the spacing between the slits in that diffraction grating shown, but often instead you will be presented with the number of lines per unit length along the diffraction grating window. So you might need to use an equation to actually calculate the slit spacing in this diffraction grating. Sometimes you'll be given the number of lines. This one says 600 lines per millimeter along this window. And so if you have a number of lines, you'll want to divide that by a unit length like meters. And if you invert that result, you will actually get the slit spacing lowercase d, which can be plugged in to your diffraction equation up top here. So for white light shining through a diffraction grating, like you see here, shining through that little window, you will notice that the central maximum is just a white light bright spot that's sent straight through. But then due to the constructive and destructive interference of these many slits, each emitting their own spherical wavelet, we end up getting a line along the first order maxima that is essentially a rainbow maxima. And the dark spots in between, we still call those minima. And of course, there are even bright fringes, maxima of rainbows that do also travel out to higher order interference levels, but those intensities of those higher order interference levels diminish significantly. And so multi-slit diffraction is actually responsible for many of the beautiful phenomena that you've seen in your daily life. For example, compact discs have this like rainbow-like sheen to them, and that's because each compact disc is etched with a very small thin line that causes light rays to come in and be emitted from each of those individual slits in such a way that we create a rainbow-like spectra of alternating bright and dark spots. This is also how structural coloration works in nature. This happens in a lot of different animals like reptiles, where you'll notice that the scales of this snake are not actually colored multicolor. It's just simply the structural nature of those scales and the repeating pattern that on a very small scale scatters light and causes it to look iridescent or rainbow-like. This happens with peacock feathers, which are structurally colored with very small distances separating the feathers or the objects within that feather that emit light at different angles with different colors and different bright spots. And this is also how many butterflies have a sort of iridescent color to them, because they have structural coloration that emits light at differing bright and dark spots depending on the angle at which you look at it. And also iridescent gemstones have structural coloration. Depending on how you look at a gemstone, it might shine one color or the other color. That's not because it has a pigment inside of the gemstone that is a certain color. Instead, it's because of the structural nature of the repeating small scale multi-slit process or multi-ridge nature of that gemstone that causes light to shine at different colors depending on different angles that you look at it. This is multi-slit diffraction. This is a diffraction grating. And so we still label the central maximum as m equals 0, and we label the next maxima as m equals -1 or +1, depending on which way you go. And there's a dark spot in between that could be calculated, but usually we'll track the bright spots for these diffraction gratings. This type of device is used in a lot of medical equipment and scientific equipment like mass spectrometers, UV-vis spectrometers, and other types of analysis equipment. We can even have another form of diffraction called single slit diffraction, where we shine coherent light toward a slit window, a diffraction filter that has only one single slit at a very small width, a very small slit opening distance. So here the idea is we're sending our light waves into this single slit, and you might think that that single slit acts as only one source of one type of wavelet, but actually light is so small that even within that slit itself, we could separate even just like the top edge or the middle edge or the bottom edge of that single slit as being a source of an individual light wavelet. And in that way, we will see that there's even an interference pattern of light waves that are being emitted from a single slit. The light waves at the top will interfere with the light waves at the bottom of that opening. And so we could visualize and measure a interference pattern by putting a screen on the other side of this single slit diffraction window. In the case of single slit diffraction, we tracked the destructive dark fringes only. We only track the minima. Notice that for single slit diffraction, we can only track the minima. That's essentially because this central maximum is a little bit wider than all the other maxima, so it's not actually necessarily like even spacing between the bright spots, so that becomes pretty tricky to calculate. But we can calculate where the dark spots will emerge. So notice in this diagram, we are tracking the dark spots in between each of the bright spots in single slit diffraction. We don't track the bright spots for a single slit. We track the dark spots, and we use this equation, which is slightly different than the diffraction equation. It's got a capital D there, and that capital D is known as the slit width. Since we have a single slit, we just want how wide that single slit is, and that will dictate something about the diffraction. And you'll also notice that m equals 0 is not possible for this equation. You must plug in m equals +1 or -1 to keep track of which dark spot you are looking at. But it's still true that trigonometry would hold if we knew our projection length L and we knew how far apart some of these features were in the interference pattern. We could still calculate their fringe spacing with reference to the central maximum. So this one is probably the hardest to visualize, and it's definitely a little bit of a trip to put your mind through, but we can divide a single slit into as many individual sources of individual wavelets that we want. Remember, a single wavefront can be cut into an infinite number of wavelets theoretically. So if I just think about 3 points of interest, the top, the middle, and the bottom of this single slit, I could think about the waves that were coming from each of those locations and the path length difference to different locations to a point of interest in space. And we would see that that path length difference, even for this single slit, for waves traveling from like the top edge of it and the bottom edge of it, there will be a phase difference, and we will find points of constructive interference and destructive interference at various points of interest along a projection screen on the right, and that gives us an interference pattern that we can measure the dark spots for. So diffraction is the bending of light around an obstacle or opening. This is different than reflection. Reflection of light is when light comes into a surface or interface and bounces back the way that it came. We've actually seen reflection for various forms of waves already. We saw reflection for Doppler ultrasound applications. We saw reflection for waves that encounter a medium, just even mechanical physical waves, as well as sound waves. So the law of reflection for light waves essentially says that the angle of incidence will be equal to the angle of reflection. In other words, the light wave will come in and hit an interface and bounce off of it at exactly the same angle that it came in at. But we need to be careful when we're talking about what angle we actually measure for a reflection event. Here, we always want to measure our angles relative to a normal axis. A normal axis, normal means perpendicular to the surface. So essentially, every time that you draw out a reflection event or a refraction event in the next slide, we want to draw our surface as like a flat, solid, horizontal line, and we want to draw our normal axis as a dashed line, perpendicular to the interface where the reflection event occurs. And this normal axis, perpendicular to the surface, will always be what you want to think about for optics experiments. Optics interactions will always be measured with their angles relative to the normal axis. You do not want to measure the angle relative to the surface or interface. You want to measure theta I, the incident angle, as the angle that the light is coming in at relative to a perpendicular axis, and theta R would be the angle relative to that perpendicular axis as well that the light comes out at. We contrast reflection with refraction, which is different. Refraction is different than diffraction, is different than reflection. And so refraction is the bending of light as it transmits from one medium to another. And you can sort of see that with this laser pointer right here. We're going to track an individual light ray for the rest of our optics experiments. And a light ray is basically just a single beam of light that we're going to track exactly directionally where it goes. And so if we take a moment and we pause, you'll notice that this light ray is coming in from air, hitting this glass prism, and it bends. It comes out, it comes through the glass at a different angle than it came in at. But we also do have a reflection event. If we draw our normal axis here, you will see that the light ray coming in hits this interface and surface, and some of it is reflected back, and it's at the exact angle that it came in at with respect to the normal axis. So that's our law of reflection right there. But some of the light is also transmitted through, and that's called refraction. And this light, as it transmits through to a new medium, will bend because it essentially changes its speed as it enters that new medium. And when it leaves the medium, it is now traveling through air again and leaves the glass prism at the same angle that it came in at. The index of refraction is essentially a measure of how light waves slow down as they enter into a new medium. And this will dictate the amount that the light ray would bend as it enters into a new medium, and is ultimately related to the speed of the light in this specific medium. For a long time, we've been prefacing that the speed of light in a vacuum is c, 3 × 10⁸ meters per second. But that speed of light is actually slower in any other medium. Any real medium other than a vacuum will cause light to slow down a little bit because the light interacts with some of the particles in the medium itself. And we use the index of refraction n to describe the ratio of the speed of light in the vacuum versus the speed of light in a specific medium. And we'll use v for that speed of light in a particular medium. N, the index of refraction, relates the ratio of these two speeds. And it's important to note that the index of refraction is unitless. And so when we think about waves traveling from one medium to another, remember what we've learned about waves in the past. Notice that as this light wave is entering into a new medium, the wavelength changes. It becomes shorter wavelength, whereas it was a longer wavelength in the low index of refraction material. And so it's shorter in the high index of refraction of material, and that's because the wave speed is slower. But the frequency of this light wave is actually going to remain constant. The frequency is dictated by the source of the waves that's generating those waves. And so to think about the index of refraction, n, we can look at some values for realistic objects and media. Like in air, the index of refraction is essentially 1. It's very similar to that of a vacuum, and you can basically plug in 1 for the index of refraction of air whenever you do this. But other materials, for example, like water, has an index of refraction of 1.33. That means water causes light to slow down a lot as light enters into the water from air or a vacuum. And glass has an even higher index of refraction. And you'll notice the index of refraction is always greater than 1. That basically means that the speed of light can never be faster than how it would be in a vacuum. And so this idea of waves reflecting or transmitting should be reminiscent of what we've already learned about waves, especially with respect to our sound waves and acoustic impedance unit. Light waves will reflect according to the law of reflection, and they will refract as well according to their index of refraction. Some light will be transmitted through to the new medium, and some light will be reflected back the way that it came. And we can calculate how much of the light intensity was reflected by thinking about the indices of refraction of the two media that the light is traveling between. Essentially, this is a lot like our acoustic impedance for a sound wave traveling from one medium to another. The intensity reflected divided by the intensity that we had incident upon that medium can be calculated as a ratio basically between the indices of refraction. And the fraction of light that was transmitted can also be calculated as the intensity transmitted divided by the incident intensity. And this is also related to the indices of refraction of the two materials. And the fraction of light transmitted and the fraction of light reflected should always end up adding up to equal 1. We'll never lose any light other than if it's transmitted or reflected under these conditions. And so we can think about how a phase shift would occur when light waves encounter different boundaries. Remember when we had a mechanical wave encountering a fixed boundary, that there would be a phase inversion in that mechanical wave. But if we had a mechanical wave traveling toward a free boundary, there would be no inversion and the wave would be reflected back partially with the same sign of displacement that it had going in. The same type of thing happens for light waves. When we are traveling toward a perfectly reflectively mirror, and a light wave hits a perfect reflective mirror, that's like a wave hitting a closed end. It will reflect back 100% of the intensity that it had with a phase shift of 180 degrees or pi radians. It basically gets phase inverted. Now, if we're traveling from low end to high end, there will be a partial transmission and partial reflection. It's not a perfect closed end or a perfect mirror. And so we could calculate the intensity reflected and the intensity transmitted, but there will still be a phase shift of 180 degrees or pi radians for going from low end to high end, low index of refraction to high index of refraction. When light passes from a high index to a low index, we would see partial transmission and reflection, except there would be no phase shift. This is like a light wave reflecting off of a free point or a lower impedance type of boundary. And finally, if light passes between media with equal N, that's essentially like traveling a light wave directly into the same medium that it's already traveling in. And so there would be no phase shift and no reflection, and all of that light would be transmitted into the new medium with the same N as the original medium. Now remember for waves that the frequency of the wave is based on the wave source. No matter what, the frequency does not depend on the medium through which the wave is traveling, but the speed, the wave speed, and the wavelength do depend on the medium through which the wave is traveling. And so if we rework our definition of the index of refraction, we will see that the speed of light in a particular medium is based on its index of refraction and the speed of light in a vacuum. So this c is the speed of light in vacuum, and if we divide it by the index of refraction, we would see that we get a wave speed that depends on the index of refraction. The wave will slow down or speed up. Its wave speed depends on the medium. And if we rework this a little bit by substituting in our frequency idea, the frequency only depends on the wave source. So the frequency of these light waves will be the same whether we're in the second medium or the first medium, but the wave speed will change, and that must mean that there must be a corresponding change in the wavelength in the medium. So as a wave passes from one medium to another, its wavelength will change in a corresponding sense to match the change in its wave speed. Now that we understand reflection and partial transmission and how light waves can reflect or refract, let's talk about a very difficult phenomena to actually wrap your head around and handle the equations for. This is one of the hardest ones in physics too, and that is called thin film interference. Thin film interference is when we have a light wave traveling toward a very thin medium such that some of the light waves reflect off of the top surface, the top interface, according to the law of reflection, and some of the light waves that are transmitted through to the next medium will reflect off of the bottom layer of that film or medium. And then as the light waves reflect off the top and transmit through and reflect off of the bottom, we'll now have two different light waves that have traveled a different length. And so they'll be slightly in phase or out of phase with each other. These light waves that reflect off the top surface and the bottom surface of a film will be somewhat in phase or out of phase with each other. And so we can calculate situations where we will have constructive interference from a thin film and destructive interference from a thin film just by the light waves reflecting off the top and bottom surface of that film. It's like the top and bottom surface each act as a individual source of waves that are slightly in phase or out of phase with each other, depending on the angle that we look at these waves. So for thin film interference, essentially we will have constructive interference when our path length difference follows this equation in light purple, and we will have destructive interference when our light waves reflect and interact with this dark purple equation. But this is a little bit tricky, so let's really get into this. Here, T is the thickness of the thin film, so you'll always want to draw a diagram that has three layers, essentially the outer layer, which has an N1 index, the middle layer, which is the film, the thin film, that has an index of refraction for itself and its own thickness, lowercase t, and the inner material of this thin film, what's below the thin film, we would call the third layer, N3. And you always want to draw out these ray diagrams as well to think about how the light waves are actually reflecting off of the top and bottom surface. Now, what makes this tricky is that light could experience a phase inversion as it encounters either of these media, the top or the bottom interface. So for each time that a light wave reflects, we got one reflection event. We got one reflection event here. This is a reflection event at the top. And we got one reflection event down here. Reflection event at the bottom, and each of those, depending on what these two end numbers are, or what these two end numbers are, each of those could have a reflection that causes a phase shift, a phase inversion of 180 degrees, or has no phase shift. It depends on if this is a bigger N or a smaller N that we're moving between. So we need to really think about how many phase inversions we will have in this thin film interference type of problem. And that means that, in other words, we will count up the number of phase inversions. And if there's one phase inversion, only, these two equations swap. You use the top equation for the destructive case and the bottom equation for the constructive case. I will give you an example for this in a sec, but I will repeat that if you have one total phase inversion due to the reflection events that you see here, then these two equations swap. But if it just so happens that when these reflection events happen, there's no phase inversions at all, having zero total, or if there's two phase inversions in total, as we go from low end to high end and a low end to another high end, there would be two total phase inversions. Then you just use these equations as is to find the constructive and destructive cases. So let's go ahead and try an example with this. This one is really tricky to understand, especially that idea about the phase inversions. But keep in mind, at the top layer, we could have a reflection event, and we could have an inversion there that causes the wave to essentially invert. Or we could have another reflection event at the bottom, maybe, depending on the ratio of these N numbers, where there's no phase inversion, and that'll matter for this thin film interference problem. Okay, so this is a thin film interference problem. Because we're asked to solve for the thinnest film thickness, that means we're solving for a t equals question mark. And so we are looking for the place where it results in a yellow stripe. Remember, dark spots, dark fringes are like no color at all. It's no light. So if you're given a specific color that you want to maximize or to show up to be able to see like a yellow spot like you see on this soap thin film right here. That means that we're going to solve for the maxima, and we're going to want to think about the two equations. We got 2t equals m lambda for constructive, and 2t equals m plus 1/2 lambda for the destructive case. And right now I'm thinking that we're going to use the constructive equation. But we need to be really careful because we need to count the number of phase inversions that this light ray will feel as it goes from air to the soap to the air again. So let's label some of our n values. N of air is 1, n of soap is 1.33, and n of air, once again, is 1. That means on the inside of this bubble I have air, there's a thin bubble layer of soap, and then on the outside I also have air. And so let's think about the number of phase inversions that we will have. This blue incident light ray comes into the interface, and there will be a reflection event. And we ask ourselves, is there going to be a phase inversion? If we travel from low n to high n, like we are here, this is n equals 1 to n equals 1.3, there is one phase inversion so far. Okay, now we also think about the next reflection event. Here, we got a reflection event on the bottom where we're going from high n to low n this time. We're going from 1.3 to 1, and that means that there will be no phase inversion for that reflection event. And so if I add up the total, that means I have one total phase inversion. And in other words, remember the rule, if I have one total phase inversion, I actually am not going to use the equations as we see here. I am going to swap them such that the top equation is used to get the destructive case when I don't have any color, these dark spots, and the constructive case for a yellow bright stripe, I would have to actually use the bottom equation here. That's what I mean when I say you have to swap them. You have to think about how many phase inversions there will be, 0, 1, or 2 total. There could be 1 at the top, 1 at the bottom. That could lead to 2, but in this case, we only have 1 total phase inversion, and so we swapped the 2 equations that we use, and now to find the constructive case for a yellow bright spot, I'm actually going to use the m plus 1/2 equation. So now the thickness could end up being solved for with m plus 1/2 times lambda, and remember, this is the lambda of the thin film itself, and you were given that lambda. It's the wavelength of light in vacuum divided by the film's index of refraction. So this is lambda 0 divided by n of the film. And all of that would be divided by 2 now. So let's go ahead and plug these numbers in and see what we get for the thinnest film that we could have. If we wanted to minimize T, right? We want a thin film, and it says the thinnest film. We would want to choose the smallest value of m that would satisfy this equation. And so we could end up plugging in 0 for m in this case. And so for the thickness of this particular soap bubble, I get 1.1 times 10 to the minus 7 meters. And so that is a very thin film that leads to this yellow part on the bubble that we can see. And so this phenomena of thin film interference is actually what you see when you're looking at Newton's rings, or the interference between 2 thin layers of glass, like between 2 microscope slides, or when you're looking at like 2 laminate sheets or 2 pieces of plastic with a small thin layer of air between them. You'll see these types of interference patterns. This is thin film interference. Or as gasoline spreads out on a surface of water or like pavement, you'll see these rings of color, which are indicative of the thickness of that thin film and how light interacts. And of course, with soap bubbles, we definitely also see thin film interference with different colors depending on the thickness of the film at that location. So thin film interference is essentially a combination of diffraction, reflection, and refraction. But in general, there's more to talk about with refraction as well. Like, how do these light waves actually bend and cause us to see things in a different location than where they truly are? Their apparent location is different than their true original location. And this is what gives rise to many optical illusions. Like if you're looking at a fish tank and it appears as if there's two fish there, but that's actually due to the way that the light rays bend as they bounce off of that fish and meet your eye. They bend at these different interaction points, and as the light rays go from water to air, they bend, and so it appears that objects are in a different location than they are. This is also how you can see certain like objects that are like disconnected if you are looking at them when they are in different media, like this layer of oil, water, and air. We see this pencil sort of seem to be broken. It's in a different apparent location depending on which layer it's in. And that's because the light rays bouncing off of that pencil are sort of traveling at different speeds and different angles until they leave the medium and reach your eyes. The law of reflection can be used to calculate how light rays will bend when they move from one medium to another. The law of reflection is also known as Snell's law, and it basically says n1 sine theta 1 equals n2 sine theta 2. We can relate the angle that these light rays are coming in at, we call that the angle of incidence theta 1, to the angle that the light rays will emerge in the new medium at, we call that theta 2, the refracted angle. And these angles will essentially be based on the indices of refraction of the two media. If these have different indices of refraction, the degree of bending will be greater. And keep in mind, just like for reflection, refraction will also measure all these angles relative to the normal axis. And so our rules still hold that we had for reflection events. You always want to draw your normal axis as a dashed line. You want to draw the surface or interface between the two materials, the boundary, as a solid line. And that will help you keep track of where you're measuring angles with respect to. We'll find that the pattern, when you calculate this out enough times, you'll get the intuition. The pattern is that light will bend toward the normal when we move from a low-end material to a high-end material. Like if we're going from air to water, the light ray will bend toward the normal. It will try to hug that normal axis closer, and the refracted angle will be smaller than the incident angle. However, when we're moving from high-end to low-end, then the light ray will bend away from the normal as it enters into that new medium. Intuitively, you can sort of think about this as like trying to push a full horizontal object from one boundary to another such that it like slows down when it enters into the new medium. And one great example is thinking about like mowing your lawn or pushing a lawnmower. As you push a lawnmower along the sidewalk, it's pretty easy to do. It moves pretty fast and doesn't have that much friction. But then when you come at an angle toward a boundary, like between grass and the sidewalk, you'll notice that this front wheel ends up catching first on the grass and sort of pulls the lawnmower at an angle and causes it to bend until all four wheels enter into the new medium. And now it's traveling at a slower speed, a little bit more friction, but all in a straight line. The similar type of thing would happen if we were moving from the lawn onto the sidewalk. We would see that our front wheel first would emerge onto the fast sidewalk and sort of push faster and cause our angle to change as we go from a high-end medium to a low-end medium. Our path would bend away from the normal. And so you can think about this in terms of light as being like a wave front with many different points on that wavefront acting as spherical wavelets, and that wavefront basically bends and moves slower in one medium versus the original medium. Essentially, the speed is very fast in the first medium, for this case on the left, and as the wavefront enters the medium of grass, the slower medium, it slows down, but the edge of the wavefront that first entered the medium goes slow first until the rest of the wavefront enters into the medium, and then the entire thing is traveling slower with a shorter wavelength, but the same frequency. So many experiments with refraction will use this semicircular refractive element. Essentially, as we send light from one medium to another, from like air into this plastic prism, we will notice that the light ray does bend, right? It's coming in at one angle and then it bends at a new angle, and we have our normal axis labeled. But as the light leaves this semicircular edge, we'll notice that the light ray actually doesn't bend. And that's because anytime we are sending a light ray from the center of a circle out toward its circular edge, the light ray will always be perpendicular to that edge. It will always be a 0-degree angle with respect to the normal axis. And in other words, the light ray will bend at the straight edge, but will not bend at the rounded edge. It will just emerge at the same angle that it came in at. So according to the index of refraction, we can send light from one medium to another, and its light ray path will bend because the light will slow down in one medium compared to another. And we discovered that the wavelength of light in a particular medium is dependent on the index of refraction, or in other words, the index of refraction is dependent on the wavelength of light. So different colors of light will actually have slightly different indices of refraction and will bend at slightly different rates. And so if we send pure white light with all of the different colors of light and different wavelengths of light inside of it toward a boundary and it experiences refraction, we'll notice that the red light waves with the longest wavelength will bend the least, while the purple light rays, or the purple wavelengths of light, will have the shortest wavelength and will bend the most. And this ultimately causes for the colors of light to separate as they experience refraction through a certain medium. And this separation of light colors is called dispersion. It's ultimately dependent on the index of refraction's relationship to the wavelength of the light. Dispersion is the spreading of different colors of light out as they experience a refraction event. And usually we will use a prism to do this. So if we shine white light toward a prism, we'll see that as it goes from air to the prism, there will be a slight separation of colors according to their different indices of refraction. And as that light exits the prism, then we can really see a pronounced difference. The red light ends up bending the least, and the purple light ends up bending the most because of how their indices of refraction are related to the wavelengths. And this is ultimately the idea that gives rise to rainbows, because there's many different water droplets. There's refraction as light comes from the sun through the air into the water, and different colors will bend at different rates. And so if there's a lot of water droplets, when we average out all of what you see for the different colors, you would see that at certain points in space there would be red light, and at other points in space there would be purple light. And this is how we end up seeing rainbows. We can have another unique phenomenon called total internal reflection, which is ultimately a result of refraction. Total internal reflection occurs when a light ray travels from a high index of refraction material to a low index of refraction of material, and is therefore completely reflected back into the original medium. There's no light that is transmitted or refracted through. It is totally internally reflected within the original medium that it was traveling in. And this will occur when we have an incident angle that exceeds the critical angle, is what we call it. This critical angle is an angle that our light ray would have to be incident upon the interface with in order to achieve total internal reflection. So we're traveling from a high end to a low end always for total internal reflection, and we can solve for the critical angle by taking the inverse of the sine of the second medium's index divided by the first medium's index of refraction. And you'll sort of see this regime activate as our incident light ray comes in at a steeper and steeper angle. Remember, we measure that angle of incidence with respect to the normal axis of the interface. Our interface is a solid line, our normal axis is a dashed line. And so as we come in at a greater incident angle, eventually the refracted angle will be 90 degrees. In other words, any of the light that was going to make it to the other side instead is like trapped within the wall of this boundary itself. All of the light that tried to make it through got bent so much that it stayed within the original material itself. And this is called total internal reflection, where our refracted angle is essentially 90 degrees. And that means that all of our light that was incident upon this interface is reflected back. Total internal reflection is the working principle behind how many devices work, including endoscopes, which essentially are used to take an image of the inside of a person's stomach or various organs in the body. Basically, we have a fiber optic cable with a light at the end of it, and we stick it down a person's throat, and that light lights up the inside of the stomach, causing light to bend every which way and bounce off the insides. And some of that light enters into this fiber optic endoscopic cable, and then we can look into that fiber optic cable and actually see what light is bouncing around inside of the stomach to actually form an image. So endoscopes work by total internal reflection. This is the same idea that's responsible for how fiber optic cables work. We can transmit light signals and information with very little losses by using fiber optic cables, where a light ray is trapped entirely within the core of a fiber optic cable that is coated with some type of outer cladding that keeps that index of refraction low and allows for total internal reflection within the material itself. Also, total internal reflection is how the sheen of various gemstones and diamonds get their unique look. Light comes in at a certain angle and then is totally internally reflected as long as its incident angle on any other boundary is above the critical angle, and this allows for light to get trapped within a gemstone and shine with extra large intensity only at certain exit angles. This is also the principle behind how retroreflectors work. They reflect back all of the light that was incident upon them, and binoculars end up using total internal reflection as well. Okay, so let's try an example of total internal reflection with a fiber optic cable. Here we have a high index core with a N value of 1.49. That's a high index material on the inside, and a low index cladding material, 1.44 on the outside of this fiber optic cable, and this causes light to experience total internal reflection. Calculate the critical angle first for this fiber optic cable, and then also we're going to discuss a little bit about how fiber optics work in a more extended application. They also have something called an acceptance angle, alpha, which is essentially the angle that would be required for light to enter into this fiber optic cable such that it does obey total internal reflection. So essentially we'll have light coming from air, entering into the core, and then being totally internally reflected by the cladding. So first, let's calculate the critical angle. We have our equation here, and it's as easy as plugging in the inverse sign of each index of refraction over one another, but you want to make sure you're very careful about which value you label as N2 and N1. Remember, N2 would be the material that the light is trying to transmit into, so that would be the cladding in this case, 1.44, and N1 is the original material that the light ray is traveling in. We're talking about like the right side of this diagram right now, and so that would be 1.49, the index of refraction of the core. And so the critical angle for this fiber optic cable ends up being about 75 degrees. That's a pretty large critical angle. Now to calculate the acceptance angle, this is basically the angle that the light ray needs to enter the core at from the air. So we want to draw a new interface here. We're talking about this vertical interface for the acceptance angle, and we'll have our normal axis being this dashed line now. Whereas previously for the critical angle between the core and cladding, we were talking about this interface and this normal axis as a dashed line. So to calculate the acceptance angle, this is basically saying any angle of light that is greater than this acceptance angle will not actually enter into the core. It will end up being lost. We need light to enter at this angle to correspond with the critical angle that we just calculated. So to figure out the acceptance angle, we're going to need to use a little bit of geometry and a little bit of Snell's law, the law of refraction. So we know that our critical angle here needs to be 75 degrees. And so that means that we have this right triangle that's sort of been drawn here. We have a right triangle right here with the real light ray being the hypotenuse. And we can then think about what this angle right here would be. This isn't the critical angle. This isn't the acceptance angle. This is just the complement of 75 degrees. This is just going to be a 15-degree angle. That random angle, I don't even know what to call it. Some complementary angle. The complementary angle will just end up being 90 minus what the critical angle was in this case. So 90 minus 75 degrees gets us 15 degrees for this interaction, this angle right here. And remember, this angle, 15 degrees, is measured relative to that normal axis, that dashed line between the air and the core. So we have the angle of 15 degrees with respect to the normal axis, and this is actually like the refracted angle. This is like a theta 2. This is the refraction angle as our light passes from air into the core of the fiber optic cable. So we can use Snell's law now to figure out what that acceptance angle alpha would be, as long as I know the index of refraction of the air and the index of refraction of the core. So let's go ahead and try to calculate alpha. And so for our acceptance angle alpha, we end up getting 22.7 degrees. That's essentially the angle that the light ray has to come in at or lower in order to actually enter the core and be totally internally reflected. So that is called the acceptance angle, and we basically used the law of refraction and a little bit of geometry to figure that out. So that'll cover everything having to do with geometric optics and wave optics. I appreciate you making it to the end of the video. I know some of these can be a little tricky, so make sure to get on top of it early. Thanks for your attention. I'll see you in the next one.